My name is Jonathan Casey. I'm a student here at Grantham University in my final term, ET 450, capstone project. There's been twists and turns, ups and downs over the past few years, but through the leadership of the university, my wife, my student advisors, and my instructors, I was able to press forward and get to this point. The project that I've chosen was a chipboard for computer automation that we will use in our industries here within the United States. My drive and my passion for this stemmed from my 7-year-old son. During my microprocessor systems and lab class, we got to play with the Arduino, do a few simple circuits, and we got to get into the more complex sides of them. I didn't know I was interested in electronics until this point. My son, he got involved with me, and he asked me one day, he said, "Dad," he said, "can you make a robot?" And I said, "I don't know," but I said, "let's try." So as I was starting into this was one of the chips, one of the components that I was actually going to use within this robotics piece. And I got to thinking, during this time, we look at our economic status here in the United States and all across the country. We're bringing more industries here back home where they belong. And our cost of living and our expenses that we have and the wages that we pay, some manufacturers and some larger industries are not going to want to pay that. So what are they going to do? They're going to run automated systems to do what was once held by manual labor, somebody that was there on the job site, there on the plant floor, walking, moving parts around and doing these sorts of things. I don't think that's the time and place that we're in right now. I think the time with our economic advances, our industrial advances, and all of our electronic advances, the technology that we have has grown too far beyond this. Of course, there's still going to be labor jobs, but things like this are our future. And so I started designing this chipboard more around this type of thing, more around the automated industry and what they would need, what they would utilize. The reason this chipboard is so critical is that it holds high yield impact, even though it's a simplistic circuit. And it actually is. But this is critical to the operation of any type of automated equipment. What this will do is act as a positioner for the robotic arm, for the belt, and for your DC motors that are operating within the system to know exactly what position they should be in order to move equipment or do welds or solders or anything along them lines. How this operates is you have an input between 3 and 32 volts DC, the way I designed this circuit. It's very cheap, very cost effective. The input voltage will then run through these two IR sensors. The differences in resistance that it will receive allows the output current signal to flow through the LM358 integrated circuit chip from output pin 4, which is the alternate current value, that will then go to your indicator light, which is the LED or buzzer, however you decide to set this up, and then into your DC motor, which will then turn, depending on if it's a stepper or stator motor or what type of motor you have, in the degree range or radius that you need for your equipment to operate properly. The operation of this specific circuit is dependent on the emission of infrared light. This type of light both emitted and read from the IR sensors that are placed on the breadboard circuit. The way that these sensors operate is the IR diode detects the emission or presence of infrared light, but its detection is inconsistent without a constant source or constant value that will allow the exact comparison to the object in range. The infrared diode will absorb the radiation and then convert it into electrical energy that this is transmitted through the circuit. The level of transmission and the current that passes is then adjusted and controlled via set point through the 10K variable resistor or potentiometer, which will give an approximate range for detection. One common type of problem with this type of circuit is the ability for the IR light to be detected from outside sources. A fix for this would be able to install a low-pass filter for the light to kind of filter out before it hits these sensors and hinders operation. Now that we understand the operation of the infrared circuit, I want to explain to you a little bit more about this specific circuit that I've designed. This circuit is designed to operate between the values of 3 and 32 volts DC. And of course, the larger the motor, the larger the voltage supply and current that needs to pass. So some adjustments within the resistors and within the variable resistor or potentiometer will need to be met and made through scientific calculation to specify your design values. This circuit contains two 220 ohm resistors, which is fed through the IR diode and through the LEDs to step down power or voltage going through the circuit that passes. A 10 kilo ohm resistor that supplies power through the LED light that will register and take it straight to ground. So you have a constant value set between the two operations of the circuit. You have a 10 kilo ohm potentiometer, which then you can adjust the values of the range of detection that you want within the circuit. Once the circuit gets power supplied through these, a current passes as it's picked up and detected. This power is then passed through the LM358 integrated circuit through pin 4, which is the output value of alternate current, goes through the LED and is emitted and tested with this LED light. The power then passes through into your DC motor. These values are calculated so that we're not careful to burn up these LED lights or the buzzer, and we still have enough power supply to go through our motor. As we test this voltage supply, we can see that we have zero current, zero voltage here at the motor, but as we trigger, we get 2.23 volts running to our DC motor, which is enough supply power to a small robot or a very small arm. And like I said before, if we need to step up the motor size in order to drive a belt or a larger arm, we have to step up our voltage source coming into the power supply, and we need to decrease our resistance on the circuit. Now that we've finished with our beta testing on our breadboard circuit, we want to take a look at the actual soldered circuit that we have. Now what I've done here is take a piece of PCB board and through-hole technology circuit. Now in actual operation for a circuit that we want to put is going to be a filmed full schematiced out board along with SMD circuits. This will make it more compact, easier to use, and a little bit cleaner of a chip to use. We have the same voltage resistance coming in. We have our value of 9 volts DC that's coming to supply into this. This is then adjusted from a potentiometer to allow the resistant voltage to be determined through the hour sensors, through the hour LED and the hour diode, which will then pick up the difference in that and actually allow that signal to pass through our LM358 operational amplifier. What this will do is allow that signal to pass out pin 4, which is an alternate voltage source supply, which will go into our indicators, which in this case is a 5mm green LED, and our buzzer, which is a 240 Hertz buzzer. What we want to do is actually have this signal that comes out, just in our simulation earlier, will supply also to a DC motor. When that signal receives high, the motor will turn. Depending on what type of motor you use and through your Arduino program, what style of program you actually write to define which degree angles that you want to happen to occur, this is all dependent on the program. But as far as operation of the circuit, I'm well within 1% tolerance range, plus or minus 1% on all components. The resistors are within 10% range of value that is specified on the package, so we know they're in proper operation conditions, and yet we get a proper test and proper functionality of a circuit. We receive our high signal, which if I can hold my fingers up here, we should get 2.84 volts, which is well within the range on a 5mm green LED to withstand 3 volts of output power supply. And you may want to use a different color or different style LED depending on what type of circuit. If you need a bigger motor and more current coming through, you'll have to adjust fire with that. But that will power supply our small DC motor in order to move an arm or a small belt. As young engineers, we step into the field with an idea, a smart goal, a set of plans, a project on our mind or in our heart that's something that we value and something that we wish to achieve. We follow the standards that's set, do our engineering calculations, and we step foot into the world and drive on. But you think something so simple as this, one small project, one idea that was put in your head, can end with something like this. To my fellow students at Grantham, to the Board of Engineers and Board of Education, all of my instructors and my student advisor, I want to say thank you. Thank you for being there for me, thank you for having me, and thank you for showing me that I can excel and gain a higher level of education.